In today's topic, we are going to cover two leftover topics, which are anti-aromatic compounds and non-aromatic compounds. Previously, we have covered aromaticity, Huckel's rule, and classification of aromatic compounds, and we are not bound to cover these two topics because our syllabus does not ask us to, but we will cover these two topics for their importance in competitive exams. So let us begin with anti-aromatic compounds. We have covered the aromatic compounds. What are anti-aromatic compounds? So if your molecule possesses 3 out of the 4 criteria of Huckel's rule, that was planarity, conjugation on each atom, and the p orbital of the lone pair orbital should be perpendicular to the plane of the molecule. If these 3 criteria are followed, and on the 4th criteria, which was 4n plus 2 rule, if it follows the 4n rule, so instead of following 4n plus 2, it follows 4n rule, then such compounds are called anti-aromatic compounds. And while aromaticity was providing stability to the molecule, the anti-aromaticity is a phenomena which provides destability to the molecules. This will increase the energy of the molecule, and that is how the molecule is going to become unstable. So there is an inverse relationship between energy and stability. Energy is always inversely proportional to stability. If anything which is more energetic, that would have less stability. If anything has more stability, let's say, then the molecule is having less energy. So there is inverse relationship between stability. So anti-aromatic compounds are going to be high in energy and less stable. These are going to be highly uncertain. They won't try to exist at all. These are so unstable that they won't exist at all. And even if they exist, they are going to be very reactive. So whenever they are existing, they will react with something. So this will happen. Even if these compounds are formed somehow, they will be extremely reactive and they will react. They do not want to exist. So this is the property of being anti-aromatic. Let us see the examples one by one. So you can see this molecule is planar. It has pi orbitals which are perpendicular to the plane. There is conjugation on each atom of the ring. The only problem is it follows 4n rule. So 2 electrons here, 2 electrons here. So if you do the count, the answer comes out to be 4. So it is not following the 4, 6, 10, 14 rule. Instead, it is following the 4, 8, 12 rule. The 4, 8, 12 rule is 4n rule, and this is for anti-aromatic compound. So this is how this molecule is anti-aromatic. The same goes for the cyclopropenyl anion. We have discussed all these examples previously. So the count is 4. So again, this molecule is also anti-aromatic. Same goes for cyclopentenyl dienine cation. So this molecule is also anti-aromatic. The same goes for cyclooctatetraene. If you do the electron count, then 2 plus 2 plus 2 plus 2. So the answer comes out to be 8. So the molecule is anti-aromatic. This is the thing when the molecule is considered planar. But somehow if the molecule planarity is disturbed, then this molecule is considered non-aromatic. This is the third category of compounds. If the molecule is not planar at all, then it is missing out the 3 leftover criteria, and this molecule would be considered non-aromatic. The same goes for cycloheptatriene, that this carbon is not the part of the conjugation, so that is why this molecule is also non-aromatic. So let us study these things with the help of this table, that if the molecule fails out in any of the 3 criteria, then this molecule is considered as non-aromatic. A good example is cyclooctatetraene. If the molecule is not planar, but if somebody is asking you whether the cyclooctatetraene is planar, then should it be anti-aromatic? The answer is yes. If it is planar, then it should be anti-aromatic because the electron count would be 8, and 8 fits the criteria of anti-aromatic compounds. Then the molecule is anti-aromatic, but if it is not planar, then it is non-aromatic. So you have to pay attention to this thing. Aromaticity we have very well covered. The best example is benzene, and the molecules which are aromatic are stable. On the other hand, molecules follows the three rules exactly the way these are mentioned in aromatic rules, but in the 4n+2 rule they follow the 4n rule, and these molecules are usually unstable. The best example is cyclobutadiene. This molecule is so unstable that it exists only below the temperature of -100 degrees Celsius. So if you freeze the molecule at this particular temperature, only then the molecule would be stable. Otherwise, if you go to higher, even a 1 degree higher than this temperature, then the molecule will react with anything. Okay, so this way we have covered the aromatic, non-aromatic and the anti-aromatic molecules. So that's it for this session. From the next session, we are going to start the unit 1B. So see you in the next session.